ready today? All right. Let me begin by asking if there are any questions. Questions? So your quiz 3 scores have been posted up on D2L, as well as I believe solutions and test problems as well. Let me know if you have any issues. If you want to see your textbook, what I can do is it's in my office. I can scan something you need to take a look at it. I apologize that if the class was smaller, we would hand things out and have you take care of it. With 250 students, handing things out takes like 20 minutes, so it'd be half the class. Okay. All right. So let's get started with some of the new material. Okay. So we were talking about work last time, and let me just make sure this is still working. That's recording. And this screen is, it's up now. Let me. There we go. Okay, so we talked about work, we talked about kinetic energy. Let's see if we remember some of the formulas we had. If I have a force F, and I have a displacement d, two vectors, then the work done by the force F displacing an object by this vector d is F dot d, the scalar product. If I write this in terms of a formula, this will be F, the magnitude of F, times d, the magnitude of d, times the cosine of the angle between the two vectors. You guys remember that last time? Okay. So we've introduced the dot product. If I have A dotted with B, so let me just review that. So I said the work done by the force F displaced by amount d. So if I have a block like this, we have a displacement like this, d, and if a force F like that. And the work done by the force F is F dot d. That's equal to F times d times the cosine of the angle between the two vectors. And then we defined, more generally, this is nothing here, A dotted with B vector was A magnitude times B magnitude times the cosine of the angle between them. And then the other formula that we worked out, or we didn't actually work it out, but we wrote down a formula, 1/2 mv squared. Okay. Any questions about this? Okay. All right. So now we are going to, let's do an example. Okay. So we'll do it together. Question is, how much work is done by a particle accelerator if an electron is accelerated from rest to 1,000 meters per second? Okay, so if you don't know this, there is a particle accelerator, or actually an ion accelerator being built just right next door. Right? It's going to be the world's most powerful heavy ion accelerator in the world. It'll be operational in probably 2021. The schedule is 2022, but it may probably be finished in 2021. Okay, that's the facility for rare isotope beams. That's where my office is located. So let's talk about this. How much work is done by a particle accelerator if an electron, so that's a negatively charged object, and it has a mass of 9.11 times 10 to the negative 31st kilograms, is accelerated from rest to 1,000 meters per second. Okay. All right, so let's think about this. We have an electron, and when we do this acceleration stuff, we're really kicking that electron. We're giving it a lot of velocity. And it's the gravity, even though gravity is acting on the electron, we're kicking it so hard that gravity is kind of negligible. Okay? What gravity would do to the electron during this very short period of time is almost nothing. So let's just say we're in outer space, and there's just this particle accelerator. The way it works, by the way, is you have maybe a negative charge here, and you have positive charge here. You'll learn about this next semester. And the electron has negative charge, and it gets pushed away from the negative charge and goes to the positive charge. The technique is you actually have positive charge here, but once it gets to where it's getting close to the positive charge, you can switch it. You can sort of frustrate it, so it never actually reaches the positive charge and it just passes through. So that's kind of the idea of a particle accelerator. And so the only force acting on the electron is the force due to the particle accelerator. Okay? And so what we're going to do is we're going to use the work energy theorem. So this was the other formula. The work done by the net force. Remember I said you can think of it two different ways. Either you take each force, you figure out the work done by force 1, take the work done by force 2, and however many you have work done by force 3. And then you add them up, because work is just a number, you can add them up. That's not effective. Or you can add up the forces together. You can say, here's force 1, here's force 2, plus force 3. You can add them as a vector sum and get the net force. And then say how much work does the net force do. Okay. They end up giving you the same answer. So it doesn't matter. It's just what I call the work done by the net force, or the sum of all of the work done by all the forces. Okay? But the formula is the work done by the net force is the change in the kinetic energy. Okay? But the electron, right, it starts from rest. So if I write down the change in the kinetic energy, this will be 1/2 mv final squared minus 1/2 mv initial squared. But if it starts from rest, there's nothing on this initial speed. 0. Okay, so then we can say that this is equal to 1/2 times the mass, which is 9.11 times 10 to the negative 31st kilograms. And then we have the final speed, 1,000 meters per second. Square that. And that comes out to about 4.56 times 10 to the negative 25 joules. Okay. And so if you ask how much work does the particle accelerator do, well, it's the only real significant force acting here. I said I'm going to neglect gravity because it doesn't really do much. So then the work done by the particle accelerator is 4.56 times 10 to the negative 25th joules. Okay? That sounds like not very much work, but typically when you have a particle accelerator, you have a lot of them that you accelerate, so that actually ends up being quite a bit. Okay. Any questions about this? Yeah. That's right. Yeah, that's a good review too. So 1 joule, you can write it several different ways, either Newton times meters, or you can break apart newtons further, and it would be 1 kilogram meters squared per second squared. Okay. Other questions? Okay. Good. I'm trying to think if I should tell you something or not, but I guess if I'm thinking about it, maybe I should tell you. Okay, so I'll tell you, if it's way off, if it's confusing, just let it go. But somebody asked about where this formula came from, and I can actually give you a better derivation of this. Oh, you can't see that. This formula, where that came from, the kinetic energy. There is a formula I talked to you about last time that the amount of energy in an object, it has mass m, remember? Einstein's theory of relativity. If it's not moving, the energy, the rest energy is just mc squared, like this, okay? But if it is moving, in other words, the momentum is not zero, so remember momentum is p, is not equal to zero. In that case, the formula becomes E is the square root of mc squared plus pc squared, okay? And so if you expand this out for the small p, you can do an little exercise in calculus. You do an expansion in small p, you end up getting a formula where you get this is approximately equal to mc squared plus a correction that's p. Okay, so I'm getting a little too complicated maybe. P squared over 2m, and then you plug in p is equal to m times v, you get 1/2 times v squared. So if you really want to know where this kinetic energy formula comes from, this is the real formula. Okay, this is how it really works. Okay. All right, I realize that was probably a little confusing. Okay, let's go on. The next thing is going to be much more related to Physics 183. We're going to talk about conservative and non-conservative forces. Okay, so it's rather straightforward. So we talked about, okay, if I find something I can lift up and down, and my phone's in my pocket, so I'll use my phone. Okay, and that's it. So we talked about, remember, the work done by, let's say the work done by gravity. So let's say my phone, it goes down. Is it doing positive or negative? Positive, right? Because gravity pushes down, and it's going down. So when you do F dot with B, they both point in the same direction and be positive. Got that? Okay. Now, if I push up, it's going up. Gravity is doing negative work. Okay. Now, what's interesting about gravity is that the amount of work gravity does going from here to there, it doesn't actually matter how it gets from here to there. It will be the same result. So let me try to convince you of that. Okay? So let's consider how much work gravity does go from here to there. So let's say it goes 1 meter. You can calculate how much force it exerts. Let's say it exerts 5 newtons. Okay, 5. I don't know how much. Let's just say 5 newtons. And it moves 1 meter, so it will do work of how many joules? 5. Okay. Now, suppose I were to actually move the phone this way. How much work is gravity doing? 0, because I'm perpendicular. Now, suppose I let it drop 1 meter. Then it will do 5 joules. Now, let's say I bring it back here horizontally. It does no work in that part. So it again does 5 joules of work. Does everybody agree? So I could do this. I can maybe go over here, bring it down, and bring it across like this. So it still do 5 joules of work. And so maybe it's clear to you, no matter how I go from here to there, it always does 5 joules of work. Does that make sense? Okay. This is an example of a force that's called conservative, in that the amount of work it does is independent of how it gets from the beginning to the end. Okay? So let's write this out. A force is conservative, meaning it conserves something, if the work it does is independent of the path taken. So you fix the beginning and the end. So here's the initial point, and here's the final point. And if I go this way, from the initial to final, let's say the work done is W1. So this will be my path number 1. And let's say I take another path like this. This will be path number 2. And in this case, the work done is W2. Then for a conservative force, we are saying that W1 is equal to W2 no matter what the paths are, as long as they connect the same initial file length. Okay. If it's not true for some case, then it's called non-conservative. Okay, everybody good on that? Now what I'm going to do is I'm going to take path 1. So we're going to go through path 1. And then we're going to reverse, thank you, and then reverse path 2. Okay, so let me try to draw what I had before. I'm going to have to slide down a bit like this. So we do path 1, look something like this. Okay, that was the beginning, this was the end, but now what I'm going to do is I'm going to go through path 2 in reverse. Like that. Okay. So if I start here, do path 1 and reverse of path 2, then does anybody know what the total work done by the force will be? 0. Yeah, 0, because if I go the reverse of path 2, I will just get negative W2. Does that make sense? Okay, so then the whole thing would give me the work done is equal to W1 minus W2, but we said they are equal, and so the work done for this closed path is 0. Okay, so just playing around with words, drawing pictures, it seems kind of pointless, kind of silly, but we just derived this, what mathematicians would say, a theorem. Okay? So we say that the work done by a conservative force going around a closed path is 0. Okay. Any questions about this? So it's very simply this. My frontier starts here. The work done by gravity when I do this is 0. The work done when I do this is 0. Okay? It starts off the same place. The work done will be 0 by conservative force. Yeah.
So that's only when the force is going in one constant direction?
That's actually the reason why gravity is conservative. It has a simple property. We'll talk about which forces are conservative and which are not. Okay. Other questions? Okay, so now let's just give you some examples of conservative forces and non-conservative forces. Okay, conservative. All right, so the main two we'll talk about, in fact, the only two we'll talk about, I'm not thinking clearly, the only two we'll talk about in this course, this semester, will be gravity, which we just discussed, but we can talk about gravity more generally. So there's more complicated formulas for gravity if you are not just at the surface of the Earth that we'll talk about later. The other one is something called a spring elastic force, or spring elastic. Let me say the word elastic so it's not confusing what this means. So we'll talk about springs. This will come in just a few minutes. Spring meaning a coil of stiff wire that you can compress or stretch. Okay. Now, examples of non-conservative forces. Okay. One very big one we'll talk about right away is going to be friction. And there's a term in your textbook when they talk about friction or air resistance is another one. These are often called, there's a term in your textbooks that I want to just mention. These are called dissipative forces. They are opposing motion. They suck out some of the kinetic energy or some of the energy of the system, and they distribute it into things that are hard to recover, like heat or something else. But another example of a non-conservative force is the force you exert with your muscles. Okay? So the amount of work you do, you actually end up doing is very complicated because your body is quite complicated. So if I, just think about the amount of work that I'm actually with my muscles doing as I'm moving it around. It requires some effort for me to do this, right? Whereas for gravity, it really doesn't do any work at all. Okay. Any questions about this? All right. Now, these, by the way, there is another conservative force that you will talk about next semester, and this is related to electrostatic force. So we'll talk about that. When you take 184, you'll talk about that. Now, for every conservative force, we can actually make a corresponding thing called a potential energy. Right? So the reason we call it conservative force is because it conserves something. But I never told you what exactly it is that it's conserving. And it's related to energy. It's actually, I'll tell you about that. So for every conservative force, there is a corresponding potential energy. We already discussed kinetic energy, now we're discussing potential energy. So let's use the symbol capital U for potential energy. Don't ask me why it's U. There's no U in potential for energy, but that's the standard thing. Okay. So potential energy. So the potential energy is the energy associated with the configuration of objects, how they are positioned or where they sit. So this may include position. For example, how high this pen is vertically, how much something is stretched, that will be relevant for the spring elastic energy. Or let's put it together, stretch or compress. And other possibilities. Other possibilities are For example, you might twist something and it might have some potential energy stored in the twisting. Okay, any questions so far? I know that's a little abstract, but we're going to do a very specific example of that now to make it concrete. Okay, so how many of you have heard of potential energy before? That's a concept. Okay. Okay, so for every conservative force, remember conservative force is one where the work done is independent of how it goes from the initial to the final. If you have a conservative force and the work it does going in a closed loop is 0, and now we can define a potential energy, and I'll give you an example of that. So let's talk about the gravitational potential energy. Okay, so the formula, so this is the gravitational potential energy, is equal to the mass times g times y. So m is the mass, g is 9.80 or 81, whatever you prefer, meters per second squared. And y, so let me say y is the vertical position. Now, it has to be relative to some reference height. So relative to some reference height. Okay, so we could take, for example, in this classroom, I could take this tabletop as y equals to 0. Or we could take the floor to be y equals to 0. You can choose where you want y equals to be 0. It's going to change the value of u, but it's not going to change any of the things we do with u. Okay? So with u, we're going to talk about differences in potential energy, and so the reference height won't matter. So let me write this out. You choose the reference height, whatever reference height you want. Okay. Often we'll take it to be the ground, but it doesn't matter. Often we take y equals 0 to be the ground. And so the idea is now if we have some reference height, reference height, this is y is equal to 0. And then if we have an object somewhere up here at some height like this, then we measure this vertical distance. That will be our y. And then the potential, the gravitational potential energy will be m times g times y. Okay, any questions about this? All right. Now, the formula that we have for kinetic energy, 1/2 mv squared, can that ever be negative? Yeah, it doesn't look like. The mass is not going to be negative. The v squared, speed squared, is not going to be negative. So it's going to be either 0 or positive. However, if you notice how with potential energy, if the object is below the reference height, we will get negative potential energy. So there's nothing wrong with negative potential energy. Okay. So if we have y is positive, then this means that u is positive. Okay. It just means that you're above the reference height. And if y is negative, this means u is negative. And there's nothing wrong with that. That's a very common question when students first encounter potential energy, that they end up with something negative. Any questions so far for these following? All right. I just want to take a peek if there are any springs back explain anything immediately, so I won't waste your time. Maybe next time. So springs, imagine in your mind. Yeah, questions? Sure, sure. Let's say we take this table in y equals to 0, and then I have this pen drop to the floor. When it gets to the floor, it'll have negative feedback. All right, so because I wasn't able to find something, there's tons of springs back there, but it'll take some time to dig it out. Just you have a coil of wire, I'm sure you've seen these, right? And it's stiff. So now it has some relaxed length to it. It naturally wants to have some length. But you can compress it, and then it's unhappy because you're squeezing it. Or you can stretch it, and it's again unhappy because we're stretching it, right? So in order to draw this kind of simply, I'm going to, so let me just write it out. So we're going to talk about the force law for a spring. So we're talking about an elastic spring. Force law for a spring. Okay, this is called Hooke's law, named after Hooke, who's a physicist a long time ago. All right, I'll write down the formula, and then I will draw, and then I'll draw the picture right afterwards so you understand. So I will write the spring force in the x direction, so I'll write it this way. This is the x component of the spring force. And the formula is pretty simple. F sub x, the x component of the spring force, is minus k times x, where x, well, I'll draw x in just a moment. So k is called the spring constant. And it's different for different springs. Now, the units for this spring constant is newtons divided by meters, because x will be in meters. The force will be in newtons, so I need something that will be newtons per meter. Now, in order for this to make some sense, let me draw the picture. So I'll show you what a relaxed spring looks like in terms of pictures. So this is a relaxed spring. And here's the, let's say one side, a wall where the spring is attached. And instead of drawing the big coils like this where it will look a little wild, let me just draw the very simple sort of accordion folded version of a spring like this. Okay. So we have a mass attached to a spring, and it has, let's say this mass has a relaxed length, like this. This is the relaxed length. That's where it goes normally. Naturally. Any questions about this? Now, we will draw a stretched spring. And the stretched spring looks like this. It's stretched. And here's where the mass now is. It's further than the relaxed length. And so the extra stretch here, we call that x. And in this case, it's positive because we made the length longer. Now, if we stretch a spring, what does it try to do? It tries to pull the mass back to its relaxed position. Okay? So as a result, because I stretch it like this, it's trying to pull me back in this direction. So that's the way that the force will go. So that's why I say that Fx, the x component of the force, is minus kx, because this is the positive x direction. And it's going in the negative x direction. Everybody following me on this? So if x is 0, and I don't stretch it at all, then the force is 0. But if I stretch it a lot, then it'll be a very strong force, because it'll be k, the spring constant, times x. Okay? And it will go in the negative x direction. It will go back towards the center, or the relaxed position. Now, if I have a compressed spring, it goes in the other direction. Compressed spring. So here I have it all bunched up like this. It's all compressed. This is where the mass is located. This is where it wants to be. And so now the x will be in this direction. It's negative. Negative value of x. And in this case, the force is going to be going in this direction. And it will be Fx is equal to minus kx. But that makes sense, that if x is negative, if I have a formula minus k times x, then the whole thing together, there's two minus signs, and so it'll be positive. And so that's why it's going in this direction. Okay. Does that make sense to everybody? So if I compress it a lot, it will really try to push out and go back towards the what's called the equilibrium point, or the relaxed point. Okay, any questions? So now that we know about the forces on a spring, there is a formula for the spring potential energy. The elastic spring potential energy. And the formula is that the spring potential energy is 1/2 k times x squared, where k is the spring constant, okay, and x is the displacement from the relaxed position. So if it's stretched or compressed, in either case it gets a positive potential energy. Okay. Any questions so far? Everybody's good? All right. Let's see. Let's maybe try to do a quicker question. All right, not a difficult one. This is a conceptual one. Okay, so the figure shown a box slides down a ramp. As the blocks slides, the work done by friction and gravity are, and here are the choices. My phone is doing funny things. questions on me right now. A. Okay, so I should draw the figure, I guess, if I say figure shown. Sorry about that. Okay, and so and I should mention there is friction so that it's not trivially zero. And the choices are A is for friction 0, gravity positive. B is that for friction it's 0, and for gravity it's negative. C, friction, it's negative, and gravity is positive. D, it's that friction is negative. For gravity, it's negative. And E, for friction, it's negative. And for gravity, it's 0. Okay? So I'm saying there is friction, it's not a frictionless surface, and so you can't say friction is 0 trivially because there's no friction. I wouldn't ask that question. Okay? All right, so I'm going to open up the polling. Go ahead and make your choice. Okay, give me another 20 seconds. Okay. Everybody made a choice? Go ahead and make a choice now if you haven't. Everybody? Okay, let's see what people said. A lot of people say C. So let's take a look at this. All right, it's pretty straightforward. Gravity goes straight down like this. That's the force of gravity, Fg, like that. The displacement goes like this. That's D. The force of friction goes in the opposite direction, Fk, for kinetic friction. So, because D and Fk go in opposite directions, the work will be negative. Okay, so it needs to be negative because the component of gravity in the direction of motion is in the same direction as the displacement. It's in this direction, it's positive. Okay, so friction negative, gravity positive. I'll see you guys tomorrow.